Okay, so last time we were talking about on Wednesday before Thanksgiving break, we were talking about joint distributions. So um, we talked a little bit about CDFs, cumulative distribution functions, right, and how to graph those based upon the PDF. And the reason why we've been talking about the PDF and the CDF is because we're interested in the joint distributions of now we're considering two random variables and seeing how they're related when they're connected together. What happens with the distribution function of those distributions that have two random variables related to together somehow. And so we started with discrete joint distributions. So we're talking about discrete joint distributions. So this is the case when you have discrete random variables. And of course, we care about the PMF of X and Y. So the notation is, we have to get used to this kind of notation. Normally, we're used to a function. You can consider it, right, as probability as a function where you take in a value, right, for the X, and you produce a probability, which is between 0 and 1. But now our inputs are no longer just single inputs. Now they're double because now we have two random variables, X and Y. And depending on what X and Y is, this really just means what's the probability that X equals the value X, right? The random variable X is equal to the value little x, and the value the value for the random variable Y is little y. So this is now what we care about. And in the example that I showed you, we had 9 different probabilities because we had X values going from 1, 2, 3, and the Y variable had values 1, 2, and 3 as well. And for each combination, 1 and 1, 1, 2, 1, 3, so on and so forth, right? We had associated probabilities. And the idea now was to figure out it was to understand. So let me just go back to that lecture. So I'm not just talking about random things here. So we discussed the probability of X and Y being jointly connected, right? And we had an example where the probability mass function for X and Y was explicitly shown, such as this. So probability of 1, 1 happening is 0.05, and so on and so forth, right? So here we had a total of 9 possibilities given our random variables that we had discretely defined. And we were given the probabilities for each of these possible outcomes. So again, all I'm stressing now is that when we have a combination, or shouldn't use the word combination, when I have a joint distribution of two random variables, what's happening is each random variable is attaining a certain value. And in attaining that value, we have a certain probability of that occurrence happening. Okay. And the way we interpreted this is now we have this idea of having two axes, right? X and Y. And now we have an additional axis. This is normally the Z axis, right? And this additional axis now gives you a three-dimensional perspective of probability. Before this, the single variable, right? We're only dealing with the two-dimensional space, where the axis here was the X variable, or the single random variable, and the vertical axis was the probability of those values being attained. So that's why the binomial looked like this. That's why the normal random variable was a bell curve, and the other kinds of random variables that we've seen also were in the two-dimensional space. But now we're headed into the three-dimensional world. So whenever we deal with joint distributions, we're dealing with a third dimension. And in relation to the joint distribution, we also talked about what's called the marginal density, or in this case, a marginal probability function here, which is just saying if I want to find what is the PMF only of X, can I get that from joint distribution? And the answer is yes. The way to do that, however, is to, if I want to find, for example, the probability that X equals 1, I have to sum up all the probabilities where X equals 1 and just add up all the probabilities for when Y equals 1, 2, and 3. So I exhaust all the values for Y, but just keep 1 fixed. And then that's exactly what I would do for 2. I want to find a probability that X equals 2. So X equals 2 is all of these values here. The Y values, I just toggle through them, 1, 2, and 3. So I toggle through all the Y values and keep the X value fixed. And I did that for the same thing for 3, and so on. And then to find the probability for Y, just the PMF just for Y, I would do the same thing. I would keep the Y, for example, probability for Y equals 1. All of these have Y equals 1. And all I would do is add up all the probabilities that toggle through all the values of X, but keep the value for Y fixed at 1. So when I add these up, I get probability being 2, and so on and so forth. So the idea is that I can figure out the marginal probability mass function, which is just really saying I can take out, or I can understand the distribution of a single variable, random variable, from the joint distribution. So if I have a joint distribution of X and Y, I can find just a probability mass function of X alone, and I can find just a probability distribution of Y alone by this formula here. So to find a probability marginal density function of X alone for discrete, this is all discrete. Whenever you see the summation, it's discrete. When you see the integral, that's when it's continuous random variables. So this notation is saying if I want to find the marginal probability mass function of X alone, I have to keep the value for X, right, fixed. But then for the Y's, I toggle through them and I add them all together. And the same thing goes for the other way. If I want to find a probability mass function just for Y, then I toggle through all the X values, right? I goes from 1 through N, all the X values, and just keep the Y fixed. Okay, so that was the idea for what we did last time. So now we'll do the same exact thing, but we're going to be doing this now for, not for, this is for discrete. Now we'll be doing it for continuous. And for continuous, we don't talk about the PMF, we talk about the PDF of X and Y. So again, this is for discrete. Let me just write this over here. So this is now continuous. And we normally use the the little F symbol. So this is gonna look something like this. So the probability that X, it's gonna look a little strange, okay? Probably that X and Y is in a certain set is equal to the integral, the double integral of x and y being in this set C, f of x, y, dx, dy. So for the continuous joint distribution, and I'm just gonna erase this part here. It's not necessarily the PDF itself. This is actually the, it's just the joint distribution. This itself here, this is the joint PDF. So right now, this looks like a lot of notation. But remember, when we talk about continuous random variables and the probabilities of continuous random variables, we speak of area. So that idea is going to come up again. What is C? C is a certain set. C is a certain set. Is a specified set. And you'll see more what that would mean. Okay. Right now, this is just like a general notation. You'll see what that means, because this is a more generalized way of expressing a general situation of finding probabilities dealing with joint distributions. So this is going to take a little bit of time. X and Y are lowercase. Yeah. So there's going to be a lot of that, right? A lot of that occurs with explaining the general notation of random variables. Uppercase letters indicate random variables, and lowercase letters regard the values of those random variables that the uppercase represent. So the uppercase are the random variables, and the lowercase are the values of that specific random variable. So little x are the values of the random variable x, big X, and little y are the values for the random variable y. This is a very, I do understand it might seem a bit confusing because it's the same letter, but for, I guess we can say, for random variables, it's case sensitive. Okay, so if it's uppercase, lowercase, there is a distinction. Maybe in other kinds of, maybe in algebra, just regular algebra, it doesn't matter, right? The X could be positive, uppercase, lowercase, doesn't matter. But in this kind of field, it does matter. Okay, so let me try to give you an idea of what this stuff is. So let me see if we have a good one here. Okay. So let me show you what I mean within a specific example. Okay. Okay, so I'm gonna give you the joint density function. Okay. The joint density function, again, a lot of these words are gonna sound the same. This is saying the joint probability. Whenever you see joint density function, it's really saying the joint probability density function. In other words, what's the joint PDF, right? So I'm going to give you the joint PDF, f of x, y. So again, this is referring to the random variable x and y being jointly distributed, jointly. And it's going to be given by a piecewise function, x plus y, very straightforward, standard, right? X plus y is a simple function. And now what gets more complicated is the description. So x plus y for what? For when 0, x, for when x is between 0 and 1, and when y is between 0 and 1. Okay, so we're going to be studying this distribution. Now, before we can begin, we have to understand what this is. The x values for the random variable x are between 0 and 1, and the y values, the values for the y random variable are between 0 and 1. We're taking all those numbers in between 0 and 1 for x and 0 and 1 for y, and we're combining them and saying that we're adding the x and the y's together. Okay? Now, what does that look like? Well, the good thing is I have good news and bad news. Bad news, I can't draw, right? So it's hard for me to do that using two-dimensional space here. But the good news is I have Maple. So with Maple, I'm able to give you a better understanding and see maybe if my attempt to draw this will make sense. So thank you, Alexandra. I'm glad you feel that way. So the idea is that this is the x, right? This is the x axis and this is the y axis. And if you're adding x values from 0 to 1 and the y values from 0 to 1, you get this piece of a graph, okay? You get this sheet. It's like a plane. It's a plane, and this is the segment or the region of the plane that we have. And so this whole region here, this whole graph here is representing the joint distribution of x and y. So you kind of have to go back to the world of multivariable calculus and understand the three-dimensional space again. Okay, so this is what's going to look like. Does everybody follow me with this? Are we okay with this? Okay, so let me go back to what I'm sharing. So this looks like this is x, this is y, this is z. This is 1, this is 1. Now, if you recall, maybe you didn't see that. Let me just quickly go back to that, just a glance. If you see here, right? If you add all the x values, right, 0 to 1, and your y values are 0, right, you get this line here. You get this line. And then the same thing goes for the other side. If your x values are all zeros, right, and you're just looking at the y values, then you get this line here, which is similar, exactly the same as this line on the other axis. Now, everything in between are the different values for x and y being non-zero. Now, what if the x and y values are both 1? So x plus y would be 1 plus 1, which give me 2. Okay, so the highest value in this probability density function, when the x values range from 0 to 1, and when the y values range from 0 to 1, the highest value here would be 2, right? I just want to make that clear. Okay. So when I draw this out, this should be really a 2. Of course, this is going to be not so good because it's not an easy thing to do. So it's going to be something like this, right? Something of this sort. Yeah, sorry guys. This is not going to work out so nicely, but I'll try my best. And at least you got to see the actual thing, okay? So this here, disregard this little line here, that's wrong. This should be like a 1 here, right? So this here is 1, this here is 1. Okay? So I tried my best. So if we had 3 variables, the highest value would be 3, or is it 2 to the n? If we had 3 variables, so the thing is, all of this stuff with the graphs depends upon what the function is. This is a simple function because we're just taking x and we're adding with y. You can make this function much more complicated, and given more variables, the level of complexity is much higher. If it was just a single variable, right, f of x equals x, x squared, x cubed, right, we have a certain standard. We have polynomial functions, we have exponential functions, right, f of x is e to the negative lambda x, right, or lambda here. We've seen these functions. Now we're in the realm of having much more freedom to it. Now we have an additional variable where we can add, subtract, raise it to the power, all these different operations. Yeah, so the reason why I'm drawing this out and giving you a visualization of this is because the first thing we always want to demonstrate, right, with probability, with just any kind of density function, mass function, is that when you sum up for discrete, when you sum up all the values, you get 1. When you integrate all the values together, you should get 1. So this condition never goes away. So we have to just check that uh, that the joint PDF is indeed a joint PDF or a PDF in the clearest sensation of it. No, 2 is not the total probability. 2 is just the value of the probability density function. The same way when you talk about probability density functions in other regards, right? And with just a single random variable, the probability density function is just a value of a probability function. It's not the value for the total probability. Okay. The idea is that if you add up all the probabilities together, whether it be a single distribution, a distribution for a single random variable or for a joint, it should always add up to 1. That's the idea. So the idea is this: look, the probability, right, that x and y is in the sample space. Okay, so this s here that I'm using here is in the sample space. In other words, what's the sample space? Well, the sample space is everything. Is from negative infinity to infinity, negative infinity to infinity. Why? Because the x values, under the assumption, right, of our x being continuous random variables, is that the continuous random variable ranges from negative infinity to infinity. And that's true for both. The idea that I want to show, what I want to show is that this equals 1. If it equals 1, we can move on. If it doesn't, then there's something wrong with the structure or the way that the probability density function is defined. But of course, this is going to work out because it has to work out. This is an example. So let's check. So again, now for those of you, I'm pretty sure most of you have taken multivariable, right? Or have seen double integrals. If not, then we will have to just go over a few things about double integration. But double integration isn't as complex as as it may seem. So what's f of x and y? Well, it's x plus y. And the values for x and y are strictly defined, right? They're between 0 and 1. So I don't have to worry about that. So this is 0. This is 0. Okay. So this is where we have to be a little bit careful. Okay. Let me see. We have to be a little bit careful here because there's a relationship between x and y. Well, x and y are connected somehow, right? So how do we account for that? Well, so this might seem a little strange at first, okay? Um, yeah, so the notation here should be 0 to 1. Yeah, I think that's fine. Okay, so the way we start this is usually from the inside out. So we kind of treat this as a single variable here. So when we look at the inner integral first, we can consider this as an iterated integral. Well, what's the integral of x plus y with respect to x only? Well, the antiderivative of x in terms of x, right, is x squared over 2. But we're going to treat y as a constant with respect to x. So this is like saying a constant. This is like saying 5. This is like saying just a number, right? A number with respect to x, the antiderivative would be yx. Do you guys see that? And then this here is being evaluated from 0 to 1. Again, this is just the inside. This is just the inside. So this outer integral is still going to be on the outside, but we're just doing with the inside first. So when I evaluate this, what happens with the x's? Well, when I plug in 1, I get a half plus y, right? And when I plug in 0, it just goes away. So I have 1/2 plus y dy from 0 to 1. Do you guys see that? So I'm looking at the inside first and then the outside. Okay? And then when I integrate this, I get 1/2 y plus half y squared over 2. And I evaluate that from 0 to 1. And when I do that, I get 1/2 plus 1/2. If I plug in 0, it goes away. And guess what I get? I get exactly what I expected, 1. Any questions about this? If you do, please let me know. This is a crucial technique on how to do or compute double integrals. Is this clear? Do you see how we're going from the inside out? How we treated the inside function with respect to x first, integrated this function with respect to x. In doing so, the antiderivative of x is straightforward. Well, the y is considered as a constant in terms of x. And we just evaluated using the definite integral. We got a new function in terms of y, and then we integrated that with respect to y, and we plugged in the values for 0 to 1, and we get 1. Yeah, like I said, this is a simple density function. So the computation behind it is very standard and simple enough. When we talk about so I think what you're referring to, Ethan, is the normal random variable. When we try to demonstrate that the density function of the normal random variable added up to, right, I think like 1, and we had to use two we have to use the double integral to show that. That is much more complicated because we had to use change of variables for that. We don't have to change any variables here. That's another thing. We didn't have to change any variables. So that's why it's a lot simpler. But what okay, so does everybody understand that the joint PDF is indeed a PDF because when you sum up all the values, which in this case is integrate all the values from for x and y together in this fashion, you get 1. And if you don't understand this, go back. So whenever you don't understand something as you get more complex with it, always refer back to what you do know. Always refer back to the more simpler case. So the more simpler case is when you don't have a joint distribution, when you have a single distribution. And what happened there? What happened with the um pardon me, with the PDF for a single random variable? Remember, this was like when x was in the sample space. If you consider the sample space, and this goes from negative infinity to infinity of f of x dx, this had to equal 1, right? This was in your exam. You have to show that you have to find the constant, right? And you have to set it equal to 1 and you solve for c. But the idea, the principle was that the PDF, when you add up all the values for x, right, which is when you integrate it, it gives you 1. We're doing the same exact thing. The only difference is now we have two random variables. The summation of x and y together, which would be the double integral, because each variable here has a specific integral connected to it, right? It has to add up to 1. And if you go back, right, if you go back again to single variable, right, and if you talk about the normal distribution, for example, you add up all the area underneath the curve, it's 1. The same thing now occurs with the joint PDF. But now, now it's not area. We've upgraded, guys. Now it's volume. So if you were to consider the plane, right? This little plane here that you saw, and you take the volume underneath it, all of this stuff underneath it, it would be 1. It has to be 1. And so instead of doing all of this, what we could have considered is that this was a cube. Well, not a cube. This was a rectangular prism. And the rectangular prism had a base of 1 and a height of 2. And so then the volume of that rectangular prism would be 2. But this plane goes right through half of it, through the diagonal. And half of 2 is 1. So you could have understood this also from a purely geometric understanding, the same way that some of you have also seen with when you did the uniform random variable, right? When you want to find the probability, you had to find the area. But now we're not dealing with area because now we're in the 3-dimensional space. Now probability is going to be really related to volume. Do you see how these things kind of correlate now? The geometric understanding of just purely shapes, curves, graphs. Now that has more of a significance because now we're talking about that geometric object or geometric characteristic, volume, area. Now we're treating that as a probability. I hope that makes sense. Okay. Great. Now, this is a PDF. It works out. This works. This is nice. Now I want to talk about the marginal. I want to talk about the marginal density. And I'm going to do this particularly of X. So I just want to know what the probability density function for X is. And how would I do that? Yeah, so let me, we usually use now, we specify, right? With the subscript, we specify what we're speaking of. So we're referencing the probability density function of X. Now go back or see or recall what that meant for discrete. What did that mean for discrete? If I want to know this, what would I have to do? I would have to fix the X and range through the Y, right? I would have to sum up all the probabilities with Y's as the Y values change, but keep the X value fixed. It's the same exact thing for the continuous aspect, right? This is for continuous, but we don't use summation notation for continuous. We use the integral. And we go through all the Y values. Do you guys understand? So it's going back to this, okay? It's like going back to this, and what we're doing is we're fixing an X value, whatever that X value is, we're fixing it and we're ranging through all the Y values. So what we get is a slither, we get a slice of this graph in the Y in this direction parallel to the Y axis. So think about having a cake or something like a cake that looks like this weird shape, right? And you're slicing slices that are parallel to the y-axis or the YZ plane. You're cutting it this way. You're taking slices and slices. That's what you're doing with this. So then what would that be? What would that look like for the specific example? So this would be the integral from negative infinity to infinity of x plus y dy, right? But of course, my y values only range from 0 to 1. So I can rewrite this integral bound 0 to 1, x plus y dy. And I'm going to now integrate this as a function of y. Well, x will be treated as a constant. So the antiderivative of x is xy plus y squared over 2 from 0 to 1. And when you plug in the values, what do you get? You get x plus a half. And that's f of x. And so this would be the probability density function for x alone. And this is when x goes from, this is for when x is between 0 and 1. Does that make sense?
So, Professor, just to clarify,
Yes.
it's just like the example from above, where you um where you put the antiderivative of x as xy because x is considered as a constant.
Yes.
Okay.
Yes. So if I were to treat this integral just the way it is, right? Forget about PDF, whatever. Just integrating this with respect to y, the x or any other variable that's not y is treated as a constant. And then you take the antiderivative or you integrate accordingly. So if it's a constant, then with respect to the variable y, then a constant, the antiderivative of a constant in terms with respect to y would be the constant times y.
Okay, thank you.
Yeah. And so then the same thing goes. So then by symmetry, what do you think the other scenario would be? What's the marginal density for y? So for y, it's the same idea. I'm integrating with respect to x, and I'm taking all of it out. I'm adding all the x values together, or integrating, I would say, right? And so that would give me just the y's. And again, it's like saying I'm looking at this sheet, this graph here, right? And I'm specifying a specific y. And what I'm doing is, I know it's going to be hard to see. I'm specifying a specific y. And what I'm doing is I'm taking this slice and I'm summing all of this up. So in reality, I'm finding the area underneath this slice. And that area constitutes as the probability of y equaling that particular y value. Do you guys understand that? So these slices here uh, cut up in this direction, right, will classify as the PDF for y alone. If I cut it this way, if I cut these slices this way, then these area slices would be constituting the PDF for the x random variable alone. And by symmetry, if you want to do the whole thing, that's fine. But by symmetry, the PDF of y would be y plus a half. And what you could do is you can check this on your own. If this is really a PDF in itself, right? What would have to be true? Negative infinity to infinity of f of y dy. This would have to be 1. And if I do that, if I check it just for y, just to see if y itself, if this PDF is indeed a PDF for y, and when I do it, I do get 1. So it works out. Do you guys see how consistent all of this is? Very consistent. Okay. Okay. Great. So I'm able to find the marginal density functions for each random variable, x and y. Awesome. Now I'm going to get into the more nitty gritty, because I'm going to ask you a very strange question, or I'm going to try to find what's the probability that x plus y, that x plus y is less than 1. Now this, think about what this means when I wrote it this in originally. So x and y here is like, it's considered a pair. right? I'm considering what x and y values when you plug in here is going to give me something less than 1. And this C is the set of such numbers that, or the condition, you can think of it. What's the condition to be in the set that we're speaking of? We're speaking of a set that contains x and y values that when you add those x and y values together must be less than 1. So I don't know if that clarifies this little notation for belongs to C. This is just saying I want to find the probability that I have x and y values that when I add them up, they give me something less than 1. And then according to the definition of this probability, finding the probability of this occurrence, according to that, the definition that I specified above is the double integral of my PDF when x plus y is less than 1, right? And I know my PDF, my joint PDF, it's just x plus y. Okay, now the hard part of this is the hard part of this is the integration bounds, is understanding the integration bounds. That's the hard part. Once you get that understood, then this just becomes a Calc 3 drill problem on solving double integrals. So the issue is, what in the world is this? What is that? X plus y less than 1? What is that? Does anybody know? The volume. No. Okay. The entire double integral does represent volume underneath the graph of f of x, y. This, when you say equals, this will be a volume. This is what the double integral is, what the double integral represents volume. The same way and analogously as when you do this, f of x dx. What does this mean? This is the area underneath, right? So always go, like I said, always go back to what you know. You know this, right? This is the area underneath f of x curve from x equal a to x equal b, right? And that what would that look like? That's a to b, and your function here, right? And this underneath is the area, is given by the integral. We don't have a single integral anymore. We have a double integral. And so the double integral now with this additional dimension is now what? Representing what? It's representing the volume underneath the graph. Analogous to the single variable when you have the area underneath the graph. Now it's the volume underneath the graph. More geometry involved. The question though is, what is this? How do you interpret this? X plus y less than 1? Well, one way to think about this, x plus y less than 1, you can say, well, I don't know what this looks like so much, but I do know, or I'm a little bit more familiar with this. Y is less than 1 minus x. What is that? Well, if I were to graph this inequality, can't I graph it? What is 1 y less than 1 minus x? Well, what is y equal to 1 minus x? Isn't that a line where the y-intercept is 1 and the slope is negative 1? So doesn't it look something like this? Right? Isn't this the dotted line? Isn't this when y equals negative 1x? But we want to find out what is y less than 1x. But what is that? Isn't this all this area underneath? And this is another example where people say, why do I need to worry about the y equals mx plus b form? Because look, it appears again. After all these years, semesters, college, whatever, you're talking about y equals mx plus b again. It's a fundamental aspect. So this is a line. This is a line. And this inequality refers to this whole area, this whole region. Now, how do we relate that to our example? Well, x plus y there's no reference to z, right? So we're not dealing with z. We're dealing with what? The x, y plane. So if I were to draw that here, right? This dotted line is y equals 1 minus x. But I want to find the region underneath it, which is this. And you see, I'm not spilling over the other side of the plane. Why? Because I'm only contained between 0 and 1 for the x and y values. So then what is this really finding then? What is this really finding? This is the volume underneath this plane under this particular domain or region. So it's going to be something like cut off here. And that volume is the volume that I'm looking for. I'm not looking for the entire volume underneath because we already did that. That's 1. That's obviously going to be 1. It has to be 1. So this probability question resulted in finding the volume underneath the curve for this region. For the region underneath the graph that's contained in this triangular region. Do you guys follow me? Do you guys see that? Any questions about that connection? If you guys don't stop me, I'll just keep. Right? Does that make sense? So now so if that makes sense, if you understand what we're considering, the double integral here, this region here is really a triangular region underneath the graph. Of course, we're not just dealing with the two-dimensional space. Now we're also dealing with that third dimension, which is a plane. And we want to find the volume underneath that plane within this triangular region. If you understand that, now the hard part of that is understanding the bounds. That's the hardest part again. Once we have the bounds, we're done. We're essentially done. We just integrate. Now this dx dy business, you can change it to dy dx as long as you keep the bounds here correct. Okay, so again, this is like kind of going back to just a review of double integrals. So if I want to integrate this region, if I want to integrate over this region, now go back and make that analogous connection to single variable. We find the area underneath an interval because there's only one dimension. So we have an interval. Whenever we take a little segment of that interval x, right? It's just an interval. Now we have a region because we have an additional dimension that we're integrating over. Now the thing is that dimension or that region that we're integrating over is a triangular region. So that makes it a little bit more interesting, right? So how do we do that? How do we integrate over this region? Does anybody remember how to do this? I'm just considering this region here, just this region here. This is the only region that I'm considering.
I can integrate from 0 to 1 minus x.
Right. Well, it depends, right? If I'm doing dx here, then my y values go from what? my y values, this depends on how you cut up the region. If you cut up the region dx dy, right, then I'm cutting it like this. I'm cutting it this way. So what do my x values go from? My x values go from 0 to what? If you look at it from this region, from this perspective, for a specific x value, right? For a specific value here, my x values go from 0 to what?
0 to 1.
No.
Oh, 0 to 1 minus x.
Now we're talking. That's right. It's from 0 to 1 minus y. 1 minus y. And the y get values go from 0 to 1. Or we can do it this way. We can cut it up this way. And when we cut it up that way, we get this instead. X plus y. Now this is dy first. dy, the y values, the y goes from 0 to 1 minus x. Do you guys see that? Do you guys see it? And then the x values go from 0 to 1. Do you guys see the difference in how I approach this inequality, this double integral with this double integral? It doesn't matter any way you slice or dice it, you get the same volume at the end. It's just that if you cut it this way, you have to be consistent with the bounds and with the order of integration. And if you cut it this way, if you cut the region this way, you have to be consistent with the bounds and the order of integration. Do you guys see that, what I'm talking about? So for the same reason why you said 0 to 1 minus x, that's if you cut it up this way vertically. Then the y's are in reference to x. But if you cut it up this way, the x's are in reference or with respect to y. That's why it's 1 minus y. But because of the symmetry, there's this symmetric understanding that 1 minus x, 1 minus y, depending upon how you cut it. And either way, it doesn't matter. Could we get a color code for the cuts? Yeah. So I'm going to put this in green. So this is going to represent the green, and that's going to represent the yellow. So the yellow here are the, this is when you vertically cut. No, sorry, horizontally cut. Horizontal cuts of triangular region. And then this is going to be the vertical cut of triangular region. So it's funny, right? It's funny how probability really becomes like an extension of calculus. It becomes an extension of integration. Because all of this stuff, just trying to find the probability of what we started with, right? X plus y less than 1, given the joint distribution of x and y, is dependent upon whether you know how to integrate. And really, though, it's not just whether you know how to integrate double integrals. It's really understanding the geometric significance of the double integral. And because you have this additional dimension, right? The region that you're integrating, it's a region that you're integrating over. It's not an interval. And so because we have a region, we have different ways to cut it. We have either vertical ways or horizontal ways to cut it. Depending upon how you choose, then it's going to affect the way your bounds are going to look like. Okay? So again, it doesn't matter which one we do. We can do both. I'm just going to do the one with the yellow. So this is going to be 0 to 1. 0 to 1 minus y, x plus y, dx dy. And then I'm going to start from the inside and work my way out. So then how do we integrate this? Well, what is this going to look like with respect to x? This is x squared over 2 plus yx, because y is considered as a constant in the integral with respect to x, okay? And then we're evaluating this from 0 to 1 minus y. I think what might help is if I color this and this. So when I color this, when I continue this, what is this going to look like? I'm replacing all the x's with 1 minus y. So I get 1 minus y squared over 2 plus y times 1 minus y. When you plug in 0 for the x's, they all go away. Then I get 1 minus 2y plus y squared over 2 plus y minus y squared. Then I cancel stuff out. This is 1/2 minus y plus y squared over 2. All I did was I divided each thing by 2 by the denominator. And I'm adding by y and subtracting by y squared. What happens? The y's here cancel. And y squared over 2 minus y squared becomes negative y squared over 2. So this equals 1/2 minus y squared over 2. Okay? So that's the inner integral. So then when I continue with my integral here, my second level of integration here, this becomes 1/2 minus y squared over 2 dy. And then when I integrate this, I get what? I get 1/2 y minus y cubed over 6, because I divided by 3. 3 over times 2 underneath will give you 6. And I'm evaluating this from 0 to 1. And when I plug in 1 for y, I get 1/2 minus 1/6. And 1/2 minus 1/6 is 1/3. Make sense, guys? So essentially, what did we figure out? We figured out that the probability that x plus y is less than 1 is 1/3. That's one way to interpret what we just found. Another way to interpret is that the area, the volume underneath that sheet or that plane within that triangular region is 1/3. Any questions? Any questions at all? Not too bad. Well, I'm glad. Different level, right? We stepped it up. Okay, and then next. Of course, we can find the expected value of x. How do you find the expected value of x in this problem? We're still continuing with the problem with the same joint distribution. How do you find the expected value? Well, what's the formula again for the expected value? Well, remember, I'm just specifying x. There's no y. So the expected value of just x? No, the expected value of x is this. From -infinity to infinity of x times f of x dx. Right? Right? That's the definition for expected value for continuous random variable x. The thing is, we found x. Didn't we find it? We found f of x, which is what? x plus a half. And this is when x is between 0 and 1. Right? So this is going to be defined as from 0 to 1 of x times x plus a half dx, which is x squared plus 1/2 x from 0 to 1 dx. Integrate. This becomes x cubed over 3 plus 1/2 x squared divided by 2, which is a fourth. This is from 0 to 1. Plug in. You get a third plus a fourth. And what do you get? You get 3 over 3, and this is 4 over 4. So you get 7/12. So the expected value of just x is 7/12. Because we're able to find the marginal density of x based upon the joint distribution. And the same thing will go for the y. Expected value of y by symmetry, it will be the same thing, right? Because of the symmetry behind it. So does this make sense, guys? It's safe to say that we will no longer be learning unique formulas for solving these probabilities, expected values, just using integral. We will no longer be learning unique formulas. What do you mean by unique? Oh, you're talking about like formulas that are for expected value that are specific to a random variable? Yeah, that those days are over. Because those are like what you've learned are like the building blocks. They're the building blocks. They're like your ABCs. So you learn the ABCs, but then as you learn language, right? There's more than just learning what A, B, C is. You have words and phrases and sentences. So now that's what's happening here. We're accumulating these different letters, quote unquote, literally actually as well. And now we're combining those two things together. We're creating a mixture. We're creating different concoctions of random variables. So based upon one random variable that's a binomial, we can do another random variable that's another binomial. Hey, what happens when we put them together? Is there a new binomial or random variable, or what kind of random variable is it? So that's what becomes more interesting to talk about. And then a lot more involved now with integration, because that's embedded inside, that's embedded within the idea of continuous random variables is integration. With discrete, it's summation. Okay. And I think we can see if we can end with one thing. So as you can start to tell, a lot of the stuff that we've talked about, right, will come back now. So we talked about what a PDF is, right, where everything sums up to 1. We've talked about finding the probabilities of specific strange sets such as this right now, but now we have a region, a two-dimensional region that we're speaking of. So this is really, whenever you see this kind of expression, we're really saying what kind of region is it? what kind of region. So this would be C. This would be like our C. Are all X and Y coordinates, all the pairs that are within this region C. And then we could talk about expected value of things again. And if you start to see where I'm headed with this, if you know about expected value, you can also figure out what? Variance, right? And then what's variance? It's expected value of x squared minus the expected value of x squared. But we know what expected value of x squared. It's 7 over 12, right? Squared. Now the question is, what is this? What's the expected value of x squared? How would you find that really quick? Integrate. Yep. Integration. But then we're integrating what? Not x f of x. We're integrating x squared f of x, right? That's all. And this is from 0 to 1. X squared. And this is what? X plus a half. So this becomes just a straightforward integration problem. From 0 to 1, this becomes x cubed plus 1/2 x squared dx. And then you're on your merry way. This is x to the 4th over 4 plus 1/2 x cubed. You bring the 3 down, this becomes a 6. This is from 0 to 1. So this is a 4th plus a 6th, which if this is times 2, this is times 3. So this is 5/12, right? So the expected value of x squared is 5/12, and you're subtracting that from 49 over 144. So then if you make this 12 over 12, this becomes 60 over 144 minus 49 over 144. So the variance of x will be 11 over 144. Okay, guys, so now we're in a different world, different level, I would say, of this world of random variables.